our experiment is HOLMES, which is an experiment aiming at a direct measurement of the neutrino mass. And so I will describe you how the experiment is designed and the status where we are. So thanks to the introduction made by Christian before the coffee break, I can go over these slides quickly. So just to remind you, our purpose is to make a direct measurement. The direct measurement is made studying the endpoint of low Q beta decays, like tritium or rhenium or holmium. And we look for the endpoint, we look for a shift of the endpoint caused by the neutrino rest mass, and which is just due to energy and momentum conservation. So there are, historically, there are two approaches for this kind of experiments. One is the one of Catherine, which is a spectrometric approach where the source is outside the spectrometer. And the other one is the approach of experiments like HOLMES or ECO or MARE before, where the measurement is calorimetric and the source is completely inside a detector, which is usually a low temperature calorimeter. There is also a third family of experiments which doesn't fit in this description, which are experiments like Project 8, and so it's not in this scheme, but it's another promising technique that we will learn about in the next days. So historically, calorimeters were motivated by the aim of avoiding some systematic effects which are observed with the spectrometers. Since in spectrometers the source is outside the detector, then everything which happens in the source, like the excitation of states or losses in the source of energy of the beta electron, can give rise to systematic effects. Of course, as we have seen, Catherine has made a lot of progresses on this, and so they are very much reduced. But still, I think it makes sense to have a different approach, which has a completely different kind of problems. And this approach is the calorimetric one, where in principle we measure all the energy released in the decay. So we actually measure the energy of the neutrinos. And in this way, all effects related to the source are removed. There are some drawbacks, which are the most important one are these two, which is the limited statistics and the pileup, which I will explain you later. Okay, so for many years, calorimetric experiment has used this isotope, rhenium-187, which was very appealing because of the very low Q and the natural abundance of about 60%. And there were two experiments in Italy, one in Genova and one in Milano, which ran for in the early 2000s, and they both reached a sensitivity on the neutrino mass of about 15 electron volts. Then after these experiments, the two experiments merged, and in a project which was called MARE, and which was aiming at achieving a sub-EV resolution on the sensitivity on the neutrino mass. But unfortunately, the difficulties of making rhenium-based detector was so high that substantially this effort didn't succeed. And gradually, the focus shifted to another process. This was an old idea of De Ruccolo and Lusignoli proposed in the 80s. And the idea was to measure calorimetrically the decay of holmium-163. This is an electron capture decay, not a beta decay. So it's a kind of beta decay, of course. But in this kind of measurements, one detects the atomic excitation of the daughter atom. So when the electron is captured, the daughter atom is left with a vacancy in the shells, and the filling of the vacancy causes the emission of radiation, which is in our case is mostly Auger electrons. And the calorimetric measurement has this kind of shape. So it's a sequence of peaks. Every peak corresponds to the binding energy of one of the shells. And these peaks have a Lorentzian shape. where the width is caused by the width of the natural width of the level which is captured, and the width is of the order of few electron volts or tens of electron volts. And these Lorentzians have tails which cannot extend to infinite, but they are truncated because of energy conservation at the Q of the transition. So at the end point, again, we find the effect of the neutrino mass exactly as for beta decay, and we have a shift of the input because of the energy of the mass of the neutrino. And it was realized that if the Q value is close to one of this peak, there is a large enhancement in the count rate and the endpoint, and this gives the possibility to have a high sensitivity on the neutrino mass. When this experiment was proposed the first time, the Q value was not really known exactly. It was just known that the Q value was so low that only the capture could happen only on the M1 shell or above. And only recently this was measured with the penning trap to be about 2.8 keV. So it's close to the M1 shell binding energy, but not as close as one would have liked to find it. So this will give a sensitivity which is not as high as one could expect for this kind of experiments. The other nice thing of this isotope is that it has a relatively short lifetime, which means that it has a high specific activity, and one needs only a limited number of nuclei to make a meaningful source. And this also means that one can introduce these nuclei in standard detectors and does not need to develop special detectors made out of holmium like it was for rhenium. So this is a calorimetric measurement, and the main drawback of calorimetric measurements is that one has to collect the whole spectrum all the time, cannot select just the endpoint electrons or decays. And this makes the detector speed a crucial parameter because when you have accidental coincidences, then you get a background at the endpoint caused by this pile-up spectrum, which is the self-convolution of the main spectrum, with an amplitude which is given by the activity of the source times the time resolution of the detectors. This is the simple expected spectrum without a second order effect, which will probably be discussed later by someone else also. The first question is how sensitive can be this approach. So this you can investigate by Monte Carlo simulations, and these are a few simulations with a few interesting parameters, experimental parameters. The first thing you can see is that the sensitivity improves with 1 over the 4th root of the statistics accumulated, and this is the most prominent feature of this plot. And the second thing is that the higher the background due to pileup, the less sensitive is the experiment. So the green one, it's 10 to the minus 3, a fraction of the total spectrum, and of the normal spectrum, and the red one is 10 to the minus 6. So if the next aim of our experiment will be 0.1 electron volt, that means to reach this kind of statistics, and you can see that these are two simulations for 10 to the minus 6 and 10 to the minus 3 that assuming conservative values for the time resolution of the detectors, that is 1 microsecond for this kind of detectors, corresponds to an activity of the single pixel of 1 becquerel or 1000 becquerel. And of course, the higher the activity, the shorter the time needed to accumulate these statistics. And even if the sensitivity for higher background it's worse, it pays out in terms of exposure needed to get to the goal of this kind of experiment. So these are two extremes. Of course, there can be other configurations which are better than these ones, but in any case, you see that you can, in principle, reach this limit, but of course, it's quite challenging. You need to have, for this configuration, which is probably not the best one, actually, it's surely not the best one, but you would need to measure 10 years with 100 millions of detectors. It's probably the biggest problem is this, not the number of detectors. Okay, so in this context, we proposed years ago, and we got funded by European Community an experiment which is called HOLMES. The idea of HOLMES was to probe this technique and see how far it can go, and start to look for the systematic effects in this approach. And HOLMES is made by microcalorimeters with holmium-163 implanted in the absorbers. There will be 1,000 channels which will be measured for 3 years. And these are the expected performance of the detectors. And you can see from these simulations that the energy resolution doesn't impact much the sensitivity. The largest impact comes from the time resolution, which is improving from red to green, and from the statistics, which is accumulated for this exposure. And the statistics, of course, grows linearly with the count rate on each detector. So this is our aim, to have a very high count rates on each detector with a time resolution of about 9 microseconds. And with this, we hope we can reach a sensitivity of around 1 electron volt or so. So this is the collaboration for this experiment. And this is a peculiarity of HOLMES, the aim of getting a very high single pixel activity. And there are 2 reasons for that. One is that in this way you can get a higher statistic in a shorter time, and this in any case it gives a better sensitivity. But also with this rate and the level of the pileup, it's such that the experiment may be almost insensitive to external backgrounds. And therefore the experiment can be carried out at above ground and not underground. And we can see from these simulations that for 300 becquerel on each detectors and this level of pileup, a background on the single pixel of about 0.2 electron volt counts per electron volt per day has a very little impact on the sensitivity. And so if we can do a bit better than 0.2, it's already negligible, the effect. While for a lower activity, the corresponding levels are much lower. So what are the sources of background? In principle, you can expect background from gamma radiation or from sources which are close to the detector, and from cosmic rays. We made a simulation for cosmic rays, and we expect this level of count rate for a single pixel. And then we can compare with our old experiment, which has similar detectors, and this had a background which was much lower than the target of HOLMES. The only remaining worrying point is this isotope, our holmium-166, long-living holmium-166, which is produced along holmium-163, and it is a beta decay, and this gives a background in the region of interest of our experiment. And by Monte Carlo simulation, we could find out that every becquerel of this holmium isotope contributes with 0.5 counts per eV per day per detector. And for our target activity per detector, this means that we have to keep the activity of this isotope more than a factor 1,000 lower than the one of holmium, which translates in this ratio for the number of nuclei. So we need, we estimate that for HOLMES, we need about 200 megabecquerel. In the detector array, there will be 300 kilobecquerels of holmium, but the efficiency of all the processes gives us this estimate of the total amount we need. And this isotope doesn't exist in nature. The most efficient way to produce it is by neutron activation. This is a sequence of reaction which gives us holmium-163. And this is the sequence of reaction which gives holmium-166. We start from erbium-162. This needs to be enriched in the material which is placed in the neutron flux, and we irradiate the erbium at ILL in France, Grenoble, where we have a reactor with a very large neutron flux, and so these are the numbers involved in this production. We made already many samples of holmium-163. we need to first purify the erbium before irradiation to avoid the production of, to minimize the production of holmium-166. And then we need to make a post-separation of holmium, chemical one, to remove a lot of other isotopes which are produced by irradiation. This process has been developed by PSI with a very high efficiency. And now we have produced the reactor, another 100 megabecquerel of holmium-163 with the activity of holmium-166 of factor 1,000 less, more or less. Then this holmium has to be introduced in the detector. This is done by a combination of mass separation and ion implantation. This is the system we have designed for our experiment. It has a ion source which produces a beam of holmium containing all holmium isotopes, in particular the 163. And then there is a magnet to select the right mass, also to reject oxides and other things. Then there is a slit to select the mass, and at the slit we expect a width of about 4 millimeters, full width of maximum. And then we have a stage for a post-focusing and a magnetic scan for uniformly implant the detector. The detector stays in the target chamber, which is another important piece of the apparatus, which I'll describe at the end. Right now we have installed the source, the ion source and the magnet and the slit. The focusing and the scanning is coming by the end of the year. Here you can see where the holmium will have to stay at the target for the spatter ion source. We have developed a procedure to extract metallic holmium from the irradiated sample. This is some thermoreduction distillation at high temperature in this furnace. And we studied the efficiency of this process, and then from this we have to produce the target for the spatter machine, for the spatter source. This is done by sintering. Okay, so this is for what concerns the detector, the implantation. Detectors are thermal detectors, so we have an absorber where we have the source and the thermometer. For this experiment, we have decided to use calorimeters which were developed by NIST for X-ray spectroscopy, which have a very high energy resolution. They are made by a transition edge sensor for measuring the temperature with an absorber on top, and they are staying on a membrane for thermal isolation. For our the TS are thermometers which measure the temperature variation by the rise of the resistance in the transition. They are very sensitive and can be very fast, and since they are low impedance, they are very suitable for multiplexing with the squid readout. We use this kind of circuit to read the sensor, and so a resistance variation is changed is transforming in a current variation to this inductance, which is coupled to a squid. So it's in the end it's a change in the flux what we measure. The detector is designed to have full containment of the electrons and photons. By Monte Carlo simulation, we decided the thickness of the detector has to be, total thickness has to be about 2 microns. So the source will be completely encapsulated in this way. We changed a bit the design of the NIST detectors because of some problem related to superconductivity. So now the absorber is beside the TS. So this square is the gold absorber where we implanted the holmium. And we have made some design and optimization and testing of these detectors without holmium using an iron 55 source or other sources. You can see this is a standard readout. It has a 4 EV resolution and 6 microseconds rise time, which are very close to our goal. So for this kind of experiment, it's very important to have a way to read more than one detectors with one line of signal, because this stays at very low temperature. So this is obtained by multiplexing, and this multiplexing readout has to provide a very large bandwidth of the order of megahertz to preserve the resolution, energy and time resolution of the detectors. This is achieved with this readout scheme, which is very complex, so I think not going very much through this. You can see a poster on this. In practice, we change the temperature variation of the absorber in an inductance variation of the squid, which is coupled to the readout circuit. And because the relation between the flux and the inductance is not linear but is periodical, we need to apply a trick which is called flux ramp modulation to linearize the response. And this in practice encodes the signal in a phase modulation of a sine at about 1 megahertz. So we have the inductance which has this kind of variation in time, and this in turn is coupled to a gigahertz resonator, and so the change in the flux is transformed in the change of the resonance frequency in the gigahertz range, so like between 4 and 8 gigahertz. So we have a resonance which shifts with time as a sine, and we detect this shift by sending a probe signal which is tuned to the frequency of resonance frequency of this resonator. When the resonator frequency shifts, then the probe signal is changing phase and amplitude, and we detect this in the end. Okay, this is one of the circuits which allows to make this kind of multiplexing with many resonances in the gigahertz domain. This designs for ohms, and everything is made by using the so-called software defined radio, which provides the tones, the probe tones to the detectors, and then detects the output signals, and by applying 2 times Fourier analysis makes all the modulation necessary to recover the original thermal signal. Okay, this is probably too complicated, but we have to match the specification of the experiment with the hardware specifications, which are mostly the frequency of the ADC of the software-defined radio. And to match this, we can play on the number of TS's which are multiplexed. In the end, we find that we can multiplex 30 TS's and have a rise time of about 10 microseconds. I will show that this rise time can give a time resolution of about 1 microsecond as we want for this experiment. The setup is quite simple. There is a HEMT here, and there is a line going up and down for RF signals. At the bottom of the refrigerator at 5 milli-K, there is a box with the detectors and the multiplexing chip. This is the test chip. And okay, we made many tests for this readout and for the various prototype of TS's. And this is one of the last results we obtained with the fluorescent source. You can see peaks from various X-ray lines. And this red one is our final baseline test design, with which we achieved a resolution of 5 eV using the whole Diacu system for ohms. And we have made a simulation to check whether this here is for 20 microsecond rise time, and this sampling we can achieve the time resolution needed for the experiment. And applying the various pulse processing, we found that we can achieve down to 1 microsecond time resolution, as close to the goal of the experiment. So now we have designed the final array for ohms. This is a linear subarray to match the size of the beam of holmium, which has this full width of maximum, so to increase as much as possible the implant efficiency. The TS's are fabricated at NIST up to this point. Then we ion implant the holmium, then we cover with another layer of gold, and then we have to remove the silicon from the back with a micromachining done by deep reactive ion etching. So we are testing this process now, and you have seen the ion implantation where we are. And now I will show you quickly the last thing, which is the system for depositing the holmium, the gold above the holmium. This is a very important component in the whole system, because it can be found by simulating the ion implant that the beam of holmium nuclei atoms removes gold from the absorber. So in the end, there is a saturation in the concentration of holmium, which can be achieved by just sending ions at 50 keV on the detectors. And to compensate this, we use a system to evaporate gold while we are implanting the holmium. So this replaces the gold which is spattered off and prevents from destroying completely the absorber, and allows us to increase the activity to the level where we want to arrive, that is about 300 becquerel. And the same system is used for depositing the final 1 micron layer. So the system is being delivered and is being tested now. You can see here there's the argon beam for spattering, and on this side the holmium beam will come and the detectors will stay here. So the holmium and the gold from the target will go on the detectors. So okay, this is my last slide. So project is a bit late, of course. This is what we plan to do in the next year. So now we have the ion implantation which is starting, and we expect next year to have the first ion implanted detector, so to start the first measurements next year with the holmium inside the detectors. So just to give you an idea, for measuring 1 month 32 pixel with the 300 becquerel activity which we are planning, we could get the sensitivity of 10 eV, but then we will grow the size of the experiment, adding the other arrays. So thank you.